Mr. Tarrou, in this math lesson, we're going to do another proof by induction. I say another one because I've done 2 other videos on this topic, the links to which are in the description. Here, we're going to be using math induction to prove that 2n factorial is greater than or equal to 2 raised to the n power times n factorial squared. A more complex situation than our first 2 other examples where we were proving a partial sum formula for a finite sum of terms and proving divisibility, where n is an element of all positive integers. Probably know this by now, but our steps for induction proofs, we're going to let p of n represent the given statement that your teacher may or may not necessarily feel that you need to do that. I'm just following the notation of the book from which I am teaching. We're going to prove that that statement works when n is equal to 1. Now that will be what we do here, but when you're doing your induction proofs, your initial value is not necessarily, doesn't have to be equal to 1. It might be some statement works when n is greater than or equal to 4. So you start checking with an n value of 4 and then go from 5, 6, 7, and 8 and so on after that by assuming that if some given statement works for some initial value, then we're just going to assume that it always works. And we're going to assume that p of k is true where k is a particular value of n, which is greater than or equal to 1, kind of just separating what we're trying to prove true from our work that is in the proof. We don't want to make the assumption or seem like we're assuming what we're trying to prove is already true. And then we're going to use that assumption to, for p of k, that's true, to then show that p of k plus 1 is also true. Get those dominoes to start falling. You know, we're not going to say, hey, this thing works when n equals 1, then n equals 2, and then n equals 3, and do a bunch of concrete examples. That's not a proof. A proof has to work for any value of n, not just 1, 2, 3, 4, 5, or whatever you happen to come up with to do an example. So that if p of k, where k is maybe equal to 5, then therefore it's going to work when k is equal to 6, which will then show that it works when k is equal to 7, and so on and so on. Those dominoes start to fall. That's your induction proof, and you'll be done. So that's going to look like this. We're going to let p of n represent this statement. And we already have the statement that n is a set of the positive integers. And we're going to consider where n is equal to 1. Or maybe you might want to write prove p of 1 is true. So what we have here for our left-hand side is that we've got 2 times 1 factorial, of course, is 2 times 1, which is equal to 2. And our right-hand side is going to be 2 to the first times 1 factorial squared. Well, look at 2 to the first is 2, 1 factorial is 1, 1 squared is 1, and we have 2 times 1, which is equal to 2. So the left-hand side is equal to the right-hand side, therefore p of 1 is true. Cool. Well, I don't want to, again, do a bunch of examples. That's not a proof. So now we're just going to say, well, this statement worked when n is equal to 1, so let's just assume that p of k is true. Step 1, step 2. Okay. Now, I've just introduced another variable just to make sure this is abundantly clear and precise. K is also going to be an element like n in that set of positive integers. Now, if this is what I'm assuming to be true, I'm going to use that to prove, I want to prove that p of k plus 1 is true. And I'm just going to go through this statement, and anywhere I see the variable k, pull it out and replace it with k plus 1. Now, that's not my proof. That's like the finish line. If I can show that the left-hand side is equal to the right-hand side using somewhere within that proof this assumed to be true fact, kind of like saying if I can show that this statement works when k is equal to 5, then automatically it works, or it will allow us to show that it's equal to when k is equal to, or that k plus 1 is equal to 6, those dominoes start to fall. If I can use this assumed information to make one side equal another side, then we have completed our induction proof. Now, what side do you start with? Whatever you feel like is going to be the simplest to, well, start from. And kind of like when you did your trig proofs back in pre-calculus, you want to start on the side that is going to allow you the most simplification, because usually when you simplify, it's easier to get to like a set ending as opposed to making things more complicated. Now, both sides of this look pretty darn complicated, but I'm going to go ahead and start on the left-hand side and see if I can't make this 2 times k plus 1, all of that factorial equal or be greater than or equal to the right-hand side. It's not required, but you will generally start on the left-hand side. So our proof here, let's clearly define it. Proof, here's where I'm starting. The left-hand side is equal to 2 times k plus 1 factorial. Can I get that to show that it's greater than or equal to 2 to the k plus 1 power times k plus 1 factorial squared? Okay, well, this is actually equal to 2 times k plus 2. And where do I go from there? Well, I need to do something with this that allows me to bring in some of my assumed to be true information, and then bringing in some information from this assumed to be true statement, then get into where this is greater than or equal to 2 to the k plus 1 power times, k plus 1 factorial squared. So I need to get this rewritten to somehow allow me to bring in some information here. Well, it would be nice if I could say, can I get a 2k factorial out of this expression that would then let me plug in some of this assumed to be true information. Okay, so let's start expanding this factorial notation. This is equal to this, which is then equal to, what do factorials do? 5 factorial is 5 times 4 times 3 times 2 times 1, and you stop at 1. So you just simply count down by 1. So 2k plus 2 factorial is 2k plus 2. And then we multiply by a factor which is 1 less. So 2 minus 1 is 1. I did say minus, yes. And then 2k plus 1 minus 1 is, ooh, that's nice, 2k. Now instead of saying 2k minus 1, 2k minus 2, 2k minus 3, and ... down to 1, because, that's what a factorial does, I'm just going to stop here and say 2k factorial. Awesome. Okay, so 2 times k plus 1 factorial is equal to this. I just simply distributed it to 2. Is equal to this. I just simply expanded a little bit of that factorial notation. Now we're going to bring in this information. So just to make sure this is clear, I'll use green. I hope it shows up on the camera. I'm going to put in this information. I'm going to replace 2k factorial with 2k times k factorial squared. Now if I do that, that's going to do a couple of things. I've just done by assumption. I've brought in some of my assumed to be true information into my proof and see if we can't we're trying to get this right-hand side to show up since we started on the left. And it's also allowing us to, we're not trying to prove that this expression is equal to this expression. We're trying to prove that it's greater than or equal to. Well, our assumption is, since it worked for when n equals 1, that 2k factorial is greater than or equal to 2k times k factorial squared. So this is assumed to be greater than what I've written here in green. Hopefully the difference between the yellow and the green is showing up. So I'm going to reiterate this. I'm going to bring the left-hand side down and say that now 2 times k plus 1 factorial is no longer equal to this expression. It was equal to the second line, but for the third line, 2k factorial is equal to or greater than, let me just highlight it, what I've written here in green. So now I've brought in the inequality notation. Now, so hopefully whatever we get, hopefully every line we go from here, this 2 times k plus 1 factorial is going to be greater than or equal to than whatever we, simplify through. Okay, so what do? Well, again, we're trying to make this 2k plus 1 show up, and we're looking at a k plus 1 factorial. Well, the only way we can get a 2k plus 1 to the k plus 1 to show up is if we have a 2 to the k, and then the plus 1 in the exponent means we need to be multiplying in another base of 2. So is there any factor where we can take out a factor of 2 to combine it with that 2 to the k power, where this first factor here has a common factor of 2. So pull that out. And let's just focus on doing one thing at a time. Don't worry too much about the rest of this expression over here. Two times 2 to the k plus 1. Bringing these together, 2 to the k times 2 is 2 to the k plus 1. Now we've got, well, let's go ahead and put this 2k plus 1 first, since multiplication is commutative. K plus 1, k factorial squared. Now, our right-hand side has some kind of factorial squared, but it's not k factorial squared, it's k plus 1. So we need to somehow make this come out to be k plus 1 factorial. Let's expand out that power of 2. And see what we got. Now remember, we're trying to make sure that this 2 times k plus 1 factorial is equal to or greater than whatever is on the rest of this proof, kind of the right-hand side. And k plus 1 times k factorial is, well, k plus 1 times k factorial is k plus 1 times k minus 1 times k minus 2 all the way down to 1. So actually these come together and create a k plus 1 factorial. Okay, bringing these together to write k plus 1 factorial. So I've got 1 k plus 1 factorial now. I just need 2. How do we get another k plus 1 factorial out of here? Because that's 2k plus 1. And if I keep counting down by 1, well, where am I going to get to k plus 1? I'm not going to try and do an expansion to do that, but what I can realize here is, as we're trying to, as long as what's on the right-hand side becomes smaller, it's still going to be by default less than our left-hand side. So we just need to come to the realization, let's get me some orange chalk out, here we go, that 2k plus 1 times k factorial, isn't that going to be greater than or equal to, what do we need here? We need another k plus 1 factorial. I need a k plus 1 times k factorial. So if I can get that k plus 1 times k factorial, I'll have another k plus 1 factorial that I can combine with this one and write it as being squared. Well, okay, so our little work here on the side, k factorial, another factor of k plus 1. This is 2k plus 1. How do we know that this factor, this first factor, is bigger than this first factor? Because k is a positive integer. It's not can't possibly be negative. So 2 times some positive number plus 1 compared to just simply that positive number plus 1, this is going to be larger. So actually, see, I'm going to take this out, this 2k plus 1 times k factorial, and replace it with k plus 1 k factorial, not because they're equal, but because this is bigger than this. This is bigger than this, and that's okay because we're looking for the left-hand side to be greater than. So if this gets even smaller, then that's still, by default, going to be greater than whatever it is I write, as long as I'm plugging in factors which are smaller, giving us a smaller product. And I'm running out of space, so we've already shown how this is equivalent to k plus 1 factorial. So this, combined with this, makes k plus 1 factorial squared. And that was our right-hand side. That is a match. Now we've shown that 2k plus 1, 2 times k plus 1 factorial is indeed greater than, well, what we set in our final statement here, our p of k plus 1 statement, as being true, and that is the end of our induction proof. So, since p of 1 is true, was proven true, and p of k plus 1 was proven true, assuming or when p of k is true, don't have a word for therefore, or the room for it, so therefore p by the principles of mathematical induction, p of n is true for all n greater than or in the set of positive integers. And that is another example of an induction proof. I'm Mr. True. Bam! Go do your homework.